This lecture is going to cover the physics of nerve cells and repolarization, depolarization, also how nerve signals propagate. I want to begin with a very brief description of the biology, how a nerve cell can create changes in potential across its membrane. I'll describe a little bit of the biology, but I want to try to emphasize the physics of that biology. Okay, we have a nerve cell. It has a membrane, inside and outside. There are three things on the membrane I want to discuss: the sodium-potassium pump, the sodium channel, and the potassium channel. So the sodium-potassium pump, or exchange pump, will move sodium ions from the inside to the outside and potassium ions from the outside to the inside. The numbers aren't equal. There's a 3-to-2 ratio. And so on average, this will move positive charge to the outside. And so the effect of this is to have the standard resting difference in charges where there's positive charge along the outside of the membrane and negative charge along the inside of the membrane. If you want to think of this in physics terms, the exchange pump is behaving very much like a battery. That is, we've described batteries as devices that somehow maintain a potential difference between one end and the other end. And the sodium-potassium pump is basically doing that. It does its best through some biology to figure out how to have a potential difference of typically negative 70 millivolts. That is, inside a cell, the potential is negative 70 millivolts, and outside the potential is 0. So there's a difference of negative 70 millivolts between inside and outside a cell membrane. Okay, so the sodium channel it's diagrammed in the lower left part of this figure. It's a channel that is designed through the magic of biology and chemistry that only sodium ions can move through it. It's typically closed, sometimes out, however it opens up, and sodium ions will flow from the outside to the inside, changing the average electric charge on the outside and the inside. And it can open and close, and it typically is triggered whether it opens and closes based on the potential difference. In that sense, it's kind of like a magic, well, whatever. Okay, so the potassium channel is something similar, except it allows only potassium ions to move through it and only from the inside to the outside. Okay, so let's talk about how this nerve cell can change. So sometimes a nerve cell will open its sodium channels, and when that happens, sodium flows from the outside to the inside, and that will change the average charge inside to a positive number. It is very easy to start blending together ideas of electric potential and charge and positive and negative. So I want to try to be pretty careful here. Inside the cell, when the sodium channel is open, sodium flows inside, and the average charge is positive on the inside. And that will result along the outside of the cell there being a collection of negative charges. And the effect of this is to change the electric potential difference. So previously, the electric potential inside the cell was lower than the electric potential outside the cell. And the way to describe that was to say the electric potential difference was negative 70 millivolts. Now, after sodium flows inside the cell, the electric potential inside this cell will be greater than outside the cell. And typically what happens is the sodium channel opens until the electric potential inside is 40 millivolts higher than the electric potential outside. Because the sodium flows really quite quickly, you can see the potential difference plotted against time. It happens in less than a millisecond. So once the electric potential inside is 40 millivolts higher than outside, the sodium channel closes, and so sodium stops flowing, and the potassium channel opens, and that's diagrammed in the middle picture. So sodium or potassium will then flow out, reducing the electric potential back to close to the negative 70 millivolts. In practice, the potential will go below negative 70, at which point the potassium channel closes, and then we have almost the resting potential again, where it's an average negative charge on the inside and positive charge on the outside. In practice, the potential difference is somewhat lower than minus 70, like minus 80, and charges will flow across the membrane. I will describe some of how to do those calculations in the homework hints, and they are also diagrammed in the examples in the textbook. Specifically, example 23.13 and 23.14, which in my copy of the textbook is on page 746 and 747. You can estimate the resistance of the membrane of charges moving across the membrane and the capacitance of the membrane, and then model the membrane as a combination of a resistor and a capacitor in a circuit. Estimate its time constant, and sure enough, that time constant describes this slow reestablishment of the negative 70 millivolt resting potential. Okay, I want to move on, however, and describe how a motor neuron signals to a muscle fiber. So a very brief description of the biology. We have a cell, a neuron cell that wants to trigger a muscle to twitch. It's connected to the muscle by an axon, a long fiber that goes from the neuron cell. It can be like as long as a meter or two, not two, to the muscle. And somehow an electrical signal goes from the cell to the muscle along this thing called an axon. So I want to just concentrate not on the biology but on the physics, specifically how that electrical signal moves along the axon. So the axon has a structure where it's somewhat thick for most of the stretch, so it's kind of like a very long cylinder, except there are short gaps in that cylinder where it's thin. Those are the nodes of Revenier. Ooh, my French isn't very good. Okay, so a very, very simple model of that is shown on the left here, where the cell body is represented as a circle, and then the long cylindrical axon is represented as a long cylinder. Along that axon, there are a combination of potassium and sodium channels that can open up and close in a way that's very similar to a nerve cell. And by opening and closing, they can increase or decrease the potential difference across that portion of the axon. And briefly, what happens is shown on the right, where sodium channels will open, allowing sodium to flow, and that creates a positive interior and negative exterior, and an increased potential difference. And that will, as that signal will trigger more sodium channels to open further along, and so that is, this sodium channel will trigger this sodium channel, or that is, this sodium channel will open, allowing sodium to flow in, which changes the potential difference over a short stretch. That change in potential difference over a short stretch will trigger the next sodium channel to open, which allows more sodium to flow in, which changes the potential over a deeper stretch, which triggers the next sodium channel to open. That is, in short, one sodium channel opens, allows sodium to flow in, which triggers the next sodium channel, which then triggers the next sodium channel, and there's a chain reaction of sodium channels being allowed to open. Following that, when the potential difference rises to the roughly 40 millivolts, the sodium channels will close, the potassium channels will open, and potassium will flow out, reestablishing the negative charge inside and the negative potential inside. And so you get this wave of where most of the axon has a negative 70, but there's a short stretch where the potential goes up to positive 40 and then back down. And that represents the stretch where there's a combination of sodium and potassium channels opening. That stretch of channels moves along the axon, and that is what nerve signal propagation is. Okay, so let's describe it a little more carefully. So there are most of the axon is thick, but there are gaps in that thickness called the nodes, and we want to describe why those nodes and why the thickness of most of it allows the nerve signal to propagate much faster than it would otherwise. What you can think of the channels being opened at the nodes, and the thick sheets as serving some purpose, which we'll describe in a moment. And so the channels open at the nodes at one node, which allows current to flow, triggering the channels at the next node to open, which allows current to flow, which triggers the channels at the third node to open, and the fourth node, and so on. Each node you can think of as being a switch. That is, the channel's opening is like a switch being triggered, and kind of like a battery. Here we're kind of sort of modeling the channels as a battery. Current flows along the inside of the ion channel, the axon channel, and then the sheath acts as a capacitor. So what happens at each node is ions flow from upstream, create a small potential difference, which somehow triggers the switch to close, which allows ions to flow, sodium to flow in and then along the middle of the axon. And the myelin sheath here acts as a capacitor, which means that there's a change in potential that we can describe using the physics of capacitors. And that changes the potential near the next node, which eventually will flip that switch. So the physics of this circuit, or of the axon, is very, very, very similar to a switch, a battery, a resistor, and a capacitor. Each node has its own switch, and so you can think of the nerve signal propagation as the first switch closing, and then the second switch closing, and then the third switch closing, and the fourth switch closing. Whoops. And the time involved is the time constant of each circuit. That is, the first switch closes, and potential difference develops, builds up across the capacitor, the first capacitor here. And how quickly it develops is related to the resistance and the capacitance of that circuit. The resistance is related to how we calculate resistance of the fluid inside the axon, and the capacitance is related to how we calculate capacitance of the myelin sheath. So I will describe those a bit in the homework hints and the example problems, and I will also point you toward the examples, example 23.13 and 23.14 in the text. Okay, we'll stop there.